Okay, so sorry about that, a little bit of a technical issue, but we're picking up here from where we left off. So the idea of a good nucleophile is we want a negative charge and we want it to be dispersed. Now, that doesn't mean that every nucleophile has to have a negative charge. In fact, there's some good nucleophiles that are neutral. Phosphines are good nucleophiles that are neutral. Most amines are neutral nucleophiles. So there's a couple exceptions to this, and the book gives a list of good and moderate nucleophiles and all this kind of stuff. And again, look, if you want to memorize that, knock yourself out, right? I'd rather understand than memorize, but whatever you guys need to do to make it through, right? So, but anyway, so what we had ended up with here is that when we have a localized O with a negative charge, it is a good nucleophile, but also a strong base. And if it can act like a base, it would rather act like a base first, okay? But there are exceptions to this. And so the idea then comes down to what happens as we contrast these two here, right? So both have an oxygen with a negative charge, right? This is a strong base, but this is a delocalized negative charge, and so we have a weaker base, right? A weaker base, but it does mean that it's a better nucleophile, right? So looking for a delocalized negative charge would probably mean that this is a better nucleophile in this case, okay? Although I got to be careful here. This will act more like a nucleophile than it will a base. This will prefer to act more like a base than a nucleophile, although it can fulfill both roles. And that's where the competition comes in, right? Which one is it more likely to do in this instance, okay? But it's not just based off of, or our decision is not just based off of the idea of whether it's a base or a nucleophile. There's other factors that go into this also, okay? But it's important to recognize the difference between a strong nucleophile and a strong base, and when these two are going to act as a base or a nucleophile, that kind of idea, okay? So we're looking for dispersed negative charges, or weak bases tend to make good nucleophiles also, okay? All right, what else do we need to do? Our leaving group, okay? Okay. Our leaving group is probably going to be the defining factor for this decision, okay? Is this going to be a primary or a secondary leaving group is what it is, okay? Now, when we have a primary leaving group, SN2 reactions are going to be our dominant reactions. When it gets to secondary, we're going to have to take a peek at this. We're going to have to make some assessments, okay? But these will not happen when it's a tertiary leaving group. Tertiary leaving groups and SN2 reactions just not going to happen for us, okay? In reality, there's actually, some discussion about this, okay? But for us, for our purposes, right, it's just not going to happen. So one of the key distinctions to make when you guys see a set of reactions is, do we have a primary, secondary, or tertiary leaving group? That's going to be one of the most important questions for you guys to ask, okay? It just so happens that with SN2, they are going to be preferred when they are a primary leaving group, okay? When you have a primary leaving group, they're going to be preferred to go SN2, okay? Secondary, depends. All right, so I think I kind of talked about this stuff enough. Let's take a look at what's going on with one of these, right? So what we need is some kind of primary leaving group. So there it is. You've got an iodine, a fantastic leaving group, okay? Fantastic leaving group. Now we need to give it a good nucleophile to come in and substitute with that. Okay, well, let's give it a maybe not a good, but let's give it a pretty good nucleophile, right? We'll throw in some cyano with it here. So here's how this works. My negative attacks the positive carbon that's attached to the leaving group. And if you make a bond, you break a bond. Okay? And so what happens here, 1, 2, 3, 4, we make our bond here to our carbon in green. And we have iodine, iodide. Okay? That's all we're doing with an SN2. The good nucleophile attacks the carbon that's bound to the leaving group. Okay? It happens all in one step, so it's concerted. Right? You guys can add some bullet points there as you need. Right? It's concerted, it happens all in one step. Right? There's 2 molecules involved in the rate determining step. Well, if it's only one step, then that has to be the rate determining step. Okay, and it's bimolecular, hence SN2. Okay? But that's all there is. We swap a leaving group for an incoming group. Extremely important chemistry. This is one of these fundamental steps that we'll see over and over and over and over and over again. Okay? In my research lab, we do this all the time, right? It seems like an elementary step. I have to be careful when I use that term. But it seems like such an elementary reaction, but it is fundamental, right? There's a lot of science and chemistry that happens off of these basic ideas here, right? So extremely important. But there's something important that we have to think about here, okay? So let's go to another example of a SN2 reaction. So let's modify this just a bit. And let's say that we do this instead. Okay? So let me walk you guys through our assessment that we know at the moment. So we look at our alkyl halide. We look at our the compound with the leaving group. So I notice that we have a good leaving group. Cool. It's secondary, so we have to really pay attention to what else is going on. Okay. We take a look at what else we have in here. We have something with a negative charge, so I have to distinguish between nucleophile or base. This negative charge is delocalized with resonance, right? So which makes it a weak base, but still a good nucleophile. So secondary leaving group, weak base, good nucleophile, we're probably going to do an SN2 reaction, okay? I'm going to start to add some components to this as we go through and kind of pick all the different groups that we have to discuss, okay? Okay, so now that I've identified that we have a SN2 reaction, we'll go through and do our mechanism here. We attack the carbon bound to the leaving group leaves, and our product will look like this. Okay? The incoming nucleophile gets added from the opposite face of the leaving group. So if my leaving group is dash, my nucleophile comes in on the wedge side, okay? Now if you think about it, this has to make sense, right? Because one thing is coming in as the other is leaving. So it can't come in on the same side as something is leaving. That would be a sterically blocked face, okay? So something has to come in from the opposite side of that it's leaving. So what we see happening here, right? What we see happening here is an inversion at that chiral center, okay? So if we have a chiral starting material, okay, we have to watch out for the chirality at the end, okay? So in this case here, it looks like we had R, and in this case here, right, it looks like we have S. Okay? I'm not saying that it necessarily inverts the stereochemistry. We have to be careful of this, but we do have to pay attention to the wedge and the dash, and we do have to pay attention to the chirality. Okay? There are some rare oddball cases where the chirality is maintained, but don't worry about those. What I need you guys to think about is if the leaving group is dashed, the incoming group is wedged. And then just you can assign stereochemistry after you have it drawn properly, okay? But the incoming group is on the opposite face of the leaving group. There's an inversion of stereochemistry that happens, okay? Cool. That's really all we need to talk about for SN2 reactions. The difficulty comes from just understanding when they do and when they don't happen. So let's do an example here real quick. See what you guys come up with. Maybe a standard example of what we might run into here. Fairly good leaving group with a bromine. It's a tertiary leaving group. Okay. Good nucleophile, weak base. Okay. So would this do an SN2? Well, no, it would not. That doesn't mean it won't react, right? In fact, from what we know at the moment, what we would say is this would probably undergo an E1, right? Because we have a weak base and a tertiary leaving group. That's kind of our setup for an E1 at this point, right? So our product would probably be some kind of elimination in this case, okay? It might even undergo an E2, although that is a fairly weak base for that to happen, but hey, strange things, right? So we would not have an SN2 reaction though in this case. And that's going to be important because eventually where we're going to build to in this semester is I'm going to ask you guys to do to build me a molecule, and I'm going to ask you guys to do it, and it's going to take more than one step. And so you guys are going to have to be clever about which reactions happen at certain parts in your synthetic pathway there, right? And so if I want to stop an SN2 reaction from happening, then I need to have a tertiary leaving group, and that's going to be one of the ways that we can select away from doing an SN2 reaction, okay? But don't worry, we'll get into that also, right? So, but the idea here is if we have a tertiary leaving group, we're not going to do SN2. For us, not going to happen, okay? Just not going to happen. All right. So I think that's kind of a good pausing point for this portion here. That seems like a good kind of place to stop for our lecture for today. Maybe a little bit shorter, but I'm hoping we come back on Wednesday and we can start to go through some of the questions that you guys have there. So SN2 reaction is extremely important, just a very, very, very common mechanistic step that we'll see over and over and over again for this, okay? But anyway, I'll see you guys on Wednesday here, I hope.